Welcome to our training, and thank you for your patience. My name is Doug James, and I have the privilege of kicking off the day by saying, glad to have you here. If you're in the room with us today, then you know that behind you is the machine that we call Stampede. And we're pretty proud of Stampede. In fact, I think I would warn you that you should take everything I say with a grain of salt, because nobody ever accused me of being objective. In fact, that's good advice for the rest of the day. We happen to be pretty proud of our facilities and our systems and the service that we provide. So I hope that shows. I hope that you hear that enthusiasm and passion in throughout the day, really throughout the 2 days. But take everything I say with a grain of salt. If you're in this room, then Stampede, the machine, is behind you. And over the course of 2 days, you'll get a chance to look at it. We'll be happy to give you a tour. And it is our signature system. This is our flagship system. This is the big beast. This is 500,000 cores. This is almost 10 petaflops of computing power. We have 1,000+ active users, 10,000 plus users registered to use it, kind of an in and out way. And so we're pretty doggone proud of it, and we hope to make you comfortable and familiar with the basics of interacting with Stampede. But I have to say, it's not the only game in town. And the world of supercomputing is changing. The days of everyone having to be a high-performance computing specialist and having to be from engineering or hard sciences, those days are changing. And maybe the right thing to do in welcoming you today is to try to give you some perspective of the way in which the world is changing. One way the world is changing is to just look at how our systems have evolved just in the last few years. As recently as 3.5 years ago, we were dismantling Ranger, which was a very, very powerful system that was, it was the fastest machine in the world in 2008 in terms of open science. Since shutting down Ranger, we have evolved to a machine that is in the top 10, Stampede, and is, a million times, arguably a million times faster than the machine that was in this very room just 4 years ago. But you know what? It's not just about computing power. It's not just about size. It's not just about memory and flops and disk space. What I'd like to do in the next few minutes is just give you a perspective for the variety that we see in the needs of the people using the computers, as well as the variety we see in the computers themselves that supply those needs. And so let's kind of walk through that. If I can find the button that pushes this, let's kind of walk through that. Right now, the Texas Advanced Computing Center, the building in which you're right now, houses about 140 people whose primary mission is to enable science, by doing the research, the support, the development, the maintenance, the design. Our job is to enable the science, the research that takes place on these systems. We're primarily an NSF-funded and UT-funded agency. We supply a high percentage of the open science computational cycles. But what I'd like to do over the next few minutes is give you some perspective for the variety and the range and the sort of the scope of the operation. We just built, I guess, let's see, it would have been, in the late 2011 timeframe, we just built the data center that houses the Stampede machine, almost 3 basketball court size room that handles Stampede. But I think it's fair to say that it's surprising when you look at all the hardware and all the software or all the equipment that's in there. And what I'd like to do is give you some sense for that. 10 megawatt data center. We're actually, the organization that you call TACC is actually housed in 2 facilities. One here we are on the north side of Austin in a facility on a campus that's part of the University of Texas, but also a major facility on campus that is our current visualization center. And what do we do? Well, we do everything from cosmology, genomics, plate tectonics, research into you know, humanities, the arts, digital arts, text analysis, you name it, we do it. This is an example of the kinds of traditional science that we do. Traditional in sense of one expects to think about modeling the cosmos when one thinks of supercomputers, and certainly these kinds of big cosmology simulations, understanding the formation of the universe, are in fact at the heart of what we do. Earthquake science, another more or less traditional application of modern high-performance computing. We right this summer, I have to say, are doing a number of simulations on a number of machines that are related to short-term weather forecasts, hurricane predictions, real-time analysis of climate data and meteorological data. I mean, this is the kind of thing that you expect to see done on a supercomputer. But more and more, what we're seeing is applications that sort of make sense when you hear them, but don't come to mind. Genomics, drug discovery, understanding, for example, the chemistry and the biology of how you know, proteins interact with other proteins, and how you know, proteins bind or do not bind on the surface of a cell. And you know, things that were unthinkable as recently or 2, 3, 4 years ago are now routine on the kind of computational power that we have. And you know, this, quote, non-traditional use of supercomputing is becoming more and more traditional. In order to do that, our hardware has had to evolve. You know, we used to think of high-performance computing, visualization, you know, getting our eyes able to absorb the information and the people, but things are changing, and I think that when you leave TACC, I hope you leave with an understanding that the landscape has changed. We now have a number of machines, a number of systems, a number of groups within the TACC organization that are designed to support the needs of communities that go beyond traditional model and simulation, traditional partial differential equations, traditional engineering and hard science. Computation is only one piece of the puzzle. You probably already appreciate the need to visualize the vast quantities of output that comes from these. But I have to tell you, just as important are storing many, many petabytes of mission critical data for our users, providing virtualization, cloud computing, providing the infrastructure that allows us to nibble at and understand data sets that are simply too big to move, where we have to put the computing engines on top of the data sets wherever they reside, and the network and the software infrastructure that makes all that possible. What we'd like to do now is turn this over to John Kaz, who is going to walk you through some of the hardware and infrastructure here at TACC that make this all possible. And it's sort of the first step in drilling down from the big picture to actually using these resources. So John Kaz is going to take it from here.
Okay, we're going to talk a little bit about the resources here at TACC, and we'll start with Stampede, our largest resource. 10 petaflop supercomputer that's been here now for about 2.5 years, coming on 2.5 this summer. Most of this computing power is in the Xeon Phi, the mic, which is a new architecture, new hardware from Intel, and then we have a little over 2 petaflops of traditional computing hardware, Sandy Bridge cores. You can read the rest of the statistics for yourself. One of the things I want you to notice though is it's not just a pure HPC platform. We have 128 GPU nodes with K20s. We also have, this I always have to look at, 16 large memory nodes that actually have 32 cores per node, not 16. A terabyte of memory. We have several users who have problems that aren't very amenable to parallelization through NPI, and so a lot of them run on these nodes either with shared memory or multiple serial tasks. And this is all funded by NSF, which we need to add to the slide. Okay, a little bit about the Xeon Phi. This is Intel's, I'd say, new architecture. We call it the mic. You might hear me refer to it as the mic, the Phi. You might hear me call it a coprocessor. Intel really does not want us to call it an accelerator. We want to call it they want us to call it a coprocessor because it runs its own OS. And in that way, it's different than a GPU in that you can actually log into it. So each mic has 61 cores. Now, in general, we'll advise you if you're using the mic to just use 60 cores and leave one for the OS because each of these cores by itself is pretty lightweight. The nice thing about the mic, though, is it's based on the x86 instruction set. So it's x86 hardware architecture, which means the same compiler that compiles for Sandy Bridge or any of the other Intel processors works for the mic. You add a different flag, it creates slightly different assembler code, but you don't need a special compiler for the mic. Any Intel compiler will do. Now, also there are a couple ways to run with the mic. You see I have up here listed 3. Really, there's 2. So the first way is offload. And running on the mic in this way is where you have a portion of your code. In general, it's going to be a multi-threaded portion because it doesn't make sense to do a single thread on the mic. The processors just aren't powerful enough. And in this portion of the code, you're going to offload it to the mic. This is pretty much the same way GPU codes work, where you have a section of your code that's in CUDA or OpenCL, and it's offloaded to the accelerator. Now, the mic has another way to run, which is native. And so in this way, you're running directly on the mic, as you can log in and run. And so you can compile a code specifically just for the mic, so all the code runs only on the mic. Now, this third model we mentioned, symmetric, is really native. It's native mixed with running on the host. So it's a heterogeneous model where you're running a native MPI code on the mic and you're running an MPI code on the host. Sometimes if you read Intel documentation, you might see it referred to as heterogeneous instead of symmetric. We're always going to call it symmetric. But today, this training is the basics about how to use Stampede. So we're just going to give you an overview of the mic hardware. We have special training to help you with programming for the mic. But first, you need to get the basics. Okay, some facts and figures about Stampede. It's been up for 2 years, over 4 million jobs, actually maybe over 5 now, 5 million now, 1 billion service units, and a service unit is 1 hour of core time. So each node, if you run on a node for 1 hour, that's 16 service units. Over 1,800 projects, 5,000 individuals have run a job, but in actuality, we really have about 1,000 active accounts each day. So there's about 1,000 users on the system trying to do something. Maybe not running a job, maybe just compiling and moving data around. Over 5,000 user tickets resolved, which many people in this room have resolved these, worked on these, and over 2,000 users attending training. This one. We've done a lot of work with other developers on the mic. Since Stampede was the first large system to have Xeon Phis, we've had to do a lot of groundbreaking. We've had to develop a lot of tools to allow our users to use the mic, a lot of processes to set it up in the queues, and we worked on a number of codes with developers. And I'd like to stress, most of these codes, the mic porting was done by the development teams. We've assisted them. I don't want to claim credit for porting this to the Xeon Phi. But this is just a listing of some of the things we have available for mic. I'd say probably the most important ones are some of the libraries, NetCDF and HDF5. And we've got a few tools to allow you to to profile your mic code. VTune, PAPI, and DDT is the debugger we have that allows you to debug your mic code. Okay, so covered Stampede. I'll go into Stampede in depth later and cover the hardware. I'm going to speak a little bit about the other resources we have here at TACC. I'll start with Lonestar. Lonestar 4 is our oldest cluster in production right now. Its scheduled end of life will be sometime this summer. We'll replace it with a new system that, so creatively, we're going to call Lonestar 5. That won't appear until probably June or July. So Lonestar 4 is also, it's a regular HPC cluster, Intel chips, InfiniBand interconnect, supports MPI and multi-threaded codes. It also has some GPU nodes and large memory nodes. And it's unlike Stampede, which is completely funded by the NSF. Lonestar was funded by several agencies, the NSF, the University of Texas Research Council. We got a bit of money from A&M, Texas Tech. I forget. There's one other school, can't remember. But it's going away. It's still a workhorse though. We still have quite a demand for it. Okay, a little bit about Lonestar 5. It'll be around 1,000 nodes, Haswell chips, FDR and InfiniBand. Well, again, we'll have GPU and large memory nodes. And we're still developing how it'll be supported through funding, but we pretty much know the specs. It'll be a nice follow-on to Lonestar 4. Okay, so those of you who are interested in big data, since that's the catchword, we have to have a big data slide. So Stampede supports big data with 30 petabytes of disk, and as it says, they're mostly full. So if any of you have run on Stampede or will run on Stampede, you'll probably run in Scratch, and that's where most of the disk is. Billions of files, you can get, well, it says sustained I/O rates of over 200 gigabytes a second, but in reality, about the best I've seen from someone running in production is 90 gigabytes per second. And every day, tens of millions of files. So there's quite a lot of turnover in the files. And while we're on big data, well, I'll talk about this later. One of the issues is the I/O subsystem and how you use it for big data. Our file system is designed for large contiguous I/O operations. If you do many small I/O operations, or you do many small parallel I/O operations, you can cause issues with the file system. In which case, if we see that, we'll contact you and we'll work with you to make it better. We have other new systems that are designed to handle this type of I/O operation. So we see our user base changing in the tools that they use and the types of codes that they run. And over the past, I'd say 2 to 4 years, we see a lot more requests for Python tools, for the use of R, for more interactive use. And so this different type of use is not really, some of this is not what Stampede was designed for. And this is what I was mentioning just a few seconds ago, that our file systems are not set up to support some of these types of run. On a small scale, they're fine, but on a really large scale, say thousands of processes, it can't handle it. You can crash the file system and impact all the other users. And so we're going to look at how we design our next system to try to support this, and I think this is going to lead into our newest system, Wrangler. This system is actually designed for this type of I/O access patterns. It uses a technology called DSSD to greatly improve I/O access times and lessen the latency overhead. And it's just come online. Allocations are available now. Early users can log in. If you're interested in this, during a break, talk to one of us and we can tell you how to get set up. And this technology appears in several different ways. I guess the first use is as a regular file system, which people who already have codes that use POSIX.io can utilize. We also have a Hadoop file system installed, and it's also set up so that it can handle block storage directly. So if you have a very I/O intensive code and you're interested in writing directly for this hardware, we support that. We have a partition in which you can run and access the DSSD directly through their block I/O APIs. And this system will support R, will support databases, we'll have Python, and this will probably be our only system that officially supports Hadoop. We used to have a system, Longhorn, that had a small set of nodes to support Hadoop. We do not support Hadoop on Lonestar or Stampede. Okay, cloud computing, another trend, not just in commercial computing, but in HPC and research. Cloud computing is coming. We will have access to 2 cloud computing resources very soon, Chameleon and Jetstream. We're partnered with the PIs to provide hardware and support. So Chameleon is a cloud testbed, and let me see if I get this straight. They're slightly different systems with slightly different purposes. Chameleon is the one that allows sort of hardcore computer science research because you can get down to the bare metal. So it'll support VMs, but it will also support researchers who want to run on the bare metal. And by that, I mean they can configure their own system to be installed on the hardware. That's a level of access that we don't grant on any of our other clusters. And as you see, the part about software-defined networking, so if you're a computer scientist interested in networking algorithms and networking research, you can use this system to play with different algorithms. Jetstream is more of your traditional cloud system. It will support VMs. We will have a library of VMs available, and users will be able to roll their own. Think of it much like Amazon's cloud system, AWS. People will be able to bring their own VMs, install, run, and we're going to support iPlant and Galaxy. Partners in this are IU in Arizona. This will be available in January. I don't think I have a date on Chameleon. I'm not sure when Chameleon. No. Okay, TACC also has a lot of Viz resources. Down on campus, we have a Viz lab. It's quite impressive. Any of the people local, if you ever get a chance, you should stop by and see it. It's in the Peter O'Donnell building. We also have a cluster here, Maverick. It's 256 nodes. Get into that. So 132 nodes. But with K40, so quite powerful GPUs. The K40s are a newer version of the K20s we have on Stampede. If you're doing visualization, data analysis, and a lot of interactive rendering, Maverick is for you. Also, if you have GPU codes you want to run, you can also use Maverick to do research. Here's just a quick picture of the Viz Lab and its layout. So the Viz Lab is actually reservable for events here on campus for people here at UT. You can reserve the conference room, you can reserve the large tile display, you can reserve the projector with the, how did I get the mouse to show up on the screen? Okay, so for those that can see the mouse, this is our large tile display, 16 by 30. So any of these resources can be reserved here at UT if you're, I think, can students reserve it or only professors, faculty, and staff? Grad students can reserve. Okay. And I have to admit, we reserve the conference room quite a bit for meetings on campus. The projector and the tiled wall are also really valuable resources, especially as we have a huge data set. You want to walk through it interactively. There's a picture of Stallion, our tiled display. Oops. So this is not the greatest picture, but you can see it here in the background. It's huge, very impressive. The software to control it is very user-friendly, easy to use. We have a touch display and the Viz portal. This is incredibly easy to use. If you're new to visualization or fooling around with these systems, you can go to the TACC visualization portal, enter your credentials, and it will start a VNC session for you on a VizNet. And so if you're using something like Visit or ParaView, you can interactively play with your data just from going through the web portal. You don't have to log in directly or set up X11 or anything else. And once it's on, it's fairly responsive. It's pretty quick. Okay, a little bit about storage. So Stockyard is our center-wide file system. All of the newer systems have Stockyard mounted as work. You'll have a scratch directory, a work directory, and a home directory. Stockyard will appear as work. Every user has a 1 terabyte quota on Stockyard. Ranch is our archive system. That's where long-term storage is. Everything's stored on tape. So you should put data on Ranch that you want to keep around, but you don't need like every day. If you need it every day, you should keep it in work or keep it in scratch. Because the access times to the tape, once it's been migrated to tape, may be minutes. Corral is our local disk-based storage system. It's only available to UT researchers, not exceed. Corral supports many collections. Here's just a listing of some of them. And so if people are interested in storing another collection, please contact us. We can work with them. Corral offers a certain amount of storage for free for everybody in the UT system, I think 5 terabytes. And anything over that, people can pay for access. And something new at TACC, now we can support HIPAA and FSMA data. We've supported ITAR on the Lonestar systems for quite a while. We'll probably support ITAR on the next Lonestar system. But up until very recently, we were not able to support HIPAA or FSMA. So these are data, well, I don't know if they're guidelines, rules, or whatever, but they're pretty severe restrictions on the storage of data and who can access it and how you access it. HIPAA is mainly associated with the medical community. Anytime you have patient data where there is identifiable information, it's considered HIPAA. We also support several classes on campus. This is a listing of, I think, all of our currently active classes. We've taught different classes. We support 3 classes if you're interested in taking formal classes in HPC. Well, the first one starts you out in programming, C and Fortran. The next one teaches you a bit about technical computing and computational methods and tools you can use. And the parallel computing class teaches you how to use MPI and OpenMP in a formal classroom setting. Also have a visualization data analysis class, which I think next year will be split into 2. So there'll be a visualization class and maybe a data analysis class, 2 separate classes. And the high performance computing with GPUs, we haven't taught that in a couple of years, but if there are requests for it, we can bring it back. Okay, a little bit about our training. This is pretty much free to, well, it's free to all university faculty, but it's also available to all of our Exceed partners. Pretty much anybody with an Exceed account can at least get online training. We'll come here in person if they're willing to travel. And this is just a quick listing of our courses. And we have had some specialized courses. And if someone requested a specific course, if we could build up enough interest, we could develop a new course. Oh, here's the Exceed part. So yes, there's also access through Exceed. Anybody with an Exceed account through the portal can pretty much sign up for training and view this online. We also support the UT system. Anyone within the UT system can come in and participate in the training too. We have an industrial affiliates program, STAR, where we have industrial partners. They also can participate in the training. So here's our acknowledgments for NSF. Stampede, Wrangler, Lonestar, Jetstream, and Chameleon are all supported by NSF. These are the awards. Oh, Chameleon comes on in August. Let me put a date in there. Remind me. Okay, that's it for the intro / quick overview, and we'll move into Stampede hardware next. Any questions? No? Is it up here? Which one? Sorry. I apologize. Operator error. All right, now we're going to get into the details of Stampede and the hardware. Okay, so if you're just if you're a programmer and you're like, well, I know how to program. I don't care what the hardware does. I program the language, it compiles it. I'm not sure I care about the details. If you program in that fashion, you may have a problem with your program running well on the hardware. So we think you should really be aware of how the hardware operates, what's available, because otherwise your programs, the compiler may not be able to optimize it well for the hardware. Now, a lot of this will be discussed later on when they talk about performance and optimization, about how you should write your program. But I just want to give you the basics of the hardware that it's running. And ask questions at any time. So high performance computing. So What we're talking about, when we mention high performance computing, we are specifically concerned with the clusters that we have here, the software, and the tools that we use to optimize the software and get it to run efficiently. And so there's a distinction between an HPC center and a data center. An HPC center is usually designed to run sort of computationally intensive codes that are very tightly connected, very tightly synchronized well. So HPC centers spend a lot of money on the network and the interconnect between the nodes to make it as fast as possible and low latency as possible. Data centers are less focused on those aspects because in general, they mostly perform many small operations in parallel that are embarrassingly parallel. There is not much synchronization needed. They mostly need throughput. So that's a little bit of difference between, I'd say, an HPC center and a data center. So Stampede, there's a picture, but for the people who are local, you walked right by it on your way in. It's right across the hall. It's supported by an NSF grant. I'm not going to read all that, but it was set up to enable petascale computing. And one of the key features of Stampede and what was in the solicitation was it required an innovative component. And so our innovative component turned out to be the mics. And that's why we have a system in which every node has a mic. This is a result of a partnership between TACC and Dell. Many of our systems are Dell's, although not all. Our latest Viz system is actually HP. But we have a very good working relationship with Dell. So when we're designing a complicated system like this, that helps a lot. Intel is also our partner since we're designing this system to use these mics before they were ever available. And actually the mics that we have are, let me see if I remember the term, pre-sales engineering products. I can't remember. They're the first mics off the line. And so there was a lot of coordination with Intel to make sure that they would work correctly when they got here and we could support them. And so here's a little bit about our data center. I think Doug mentioned this earlier. So to support this system, Stampede, we had to greatly expand our data center. So here in this green portion, that was our older system, Ranger. That was the original building, the original data center. And so once we knew we had Stampede, we had plans to expand our data center, but they had to be greatly accelerated. So pretty much they built this data center in a year. The data center across the hall in the room you're in now. It's quite impressive. But as much space as this new data center takes, there was more square footage in the supporting facilities. So to support Stampede, we also had to build new chillers, a new power supply system. And that's what's on this map out here in the back. And this is set up solely to support the machine room here in Stampede. And so it's a little bit about the way it works. We pump 3,000 gallons per minute, chilled water, and provide 6.5 megawatts of power. Stampede itself, I think, takes about 3 on an average day. And if we're running something like HPL, it can go up to 4. This is just a quick layout of what the room looks like. So what you see here, all these blue boxes are the actual compute nodes. The yellow boxes are the switches. The dark purple is I/O. And so you might be thinking, well, what are these green boxes? They seem to take up a lot of space. Well, the only way we can pack this much hardware into that room this densely is we have something called in-row coolers. That's what this IRC means, in-row cooler. It's basically an air conditioner. It sits there and there's a hot aisle and a cold aisle. And the hot air on the hot aisle goes to these in-row coolers and gets exhausted out the other side. It gets chilled. So we don't just have we don't just have chilled water to cool the air in the whole room, we have chilled water running to each of these in-row coolers to take care of the heat. And here's a picture of the infrastructure facilities we had to build. And so here you can see all the piping, that's where the pumps are. Outside here are the chillers that run to keep the water cold. Here's our electrical facility to handle the power. And you might be wondering what this big empty room. This is actually the inside of this tank. So what we have here is we have an insulated tank so that we chill more water than we need and we store it. And then during the middle of the day when it's hottest and the price of electricity is highest, we quit running these chillers. And then we use the water in this tank to cool the system. Then after the sun goes down and the price of electricity drops, the chillers kick back on and chill water for the machine room and the tank. So Stampede debuted number 7 on the top 500. The top 500 is a listing of HPC systems that run a benchmark called HPL. It's been around for 20 some odd years now, I think, 20 plus. We started at number 7. I think we slipped to number 10, 11. I haven't checked the latest one. And this is just basically a measure, almost a measure of peak performance. It runs an application that gets anywhere from 70 to 90% of peak. Now, this is uncommon for any regular application. Most applications will be 5 to 10% if they're tuned well. If they're more than 10%, they're tuned very well. Okay, so Stampede was a $27 million acquisition. So before, I think I mentioned a number of 52 million and 50 some odd million. Half of that cost is for maintenance and upkeep over the 5 years of Stampede's running. 6,400 nodes, and most of those nodes are the same. They're 2 Sandy Bridge sockets with a mic. 128 have GPUs, 16 are large memory nodes. The larger memory nodes are a little bit different. As I said before, they have 32 cores, but they also have 4 sockets. They needed 4 sockets to be able to pump the memory up to a terabyte. And it's all connected with Mellanox InfiniBand. 56 gigabits per second and pretty low latency, around a microsecond. So a little bit about each processor. So as you look at this, if you ever think about the mics in running on the mic and the host, keep this in mind. The architectures are quite different. The number of cores is quite different. The clock speed is different. The number of threads you can run per core is different. But there's a trend here. So this Xeon Phi supports 61 cores. The next version of the mic will support over 60. The newer Haswell chips, at least the ones I've seen, support up to 18 cores per chip. So these architectures are converging. The main thing to note, though, when you're programming for these different architectures is that since this one has many more cores at a slower clock speed, you really have to have a code that can take advantage of multi-threading. You don't want to run 61 or 60 or 120 MPI tasks on the mic. You just want to run a few tasks in multiple threads. While on this side, running 1 MPI task per core is perfectly acceptable because it's a fewer number of cores and there's a higher bandwidth off the node per core. Also, a little bit of difference in the vector unit. So the vector unit on the Xeon Phi per core is twice as large as the vector unit on the Sandy Bridge processor. And so on the Xeon Phi, multi-threaded and vectorization are extremely important. if your code's not optimized for those two things, it will run very, very poorly. Okay, so what is a mic? I'm repeating myself. x86 architecture. It's got much more silicon dedicated to floating point performance. That's what it's designed for. So the vector units are twice as wide as on a regular chip. Now, what it's done is it's gotten rid of some things that have made life easier for you on regular Intel chips. The out-of-order execution and branch prediction. So on a regular chip, the hardware does a lot of things for you to make sure your code always runs in the optimal path, sort of through the assembly. Where on the mic, this won't happen. So if you have a lot of if statements, you really need to optimize them for the mic. Also, you've got fast access to memory on the mic, faster access than maybe on the Sandy Bridge, but then you're sharing that among 61 cores and 4 hardware threads per core. And unlike the Sandy Bridge processor, on the mic, you need to run 2 hardware threads if you want to get anywhere near its full potential, because each hardware thread can issue a vector operation only every other clock. So it's a little bit different to program for. The nice thing is, almost everything you do to improve performance on the mic translates directly to all the other Intel chips. Every project I've seen where they've ported their code to the mic and optimized for the mic, they're trying to make it better than the host. Well, it also improves the way it runs on the host. So that's a nice side effect. Okay, a quick look at the mic architecture. The cores are laid out in a ring fashion. So there's a ring network that connects all the cores. You can see it here. Each core has its own L1 and L2 and then goes out to main memory. And so here's a chart sort of outlining what I said earlier, the differences between the mic and the host. 2 sockets, 1 socket, 8 cores, 61 cores, 2.7 gigahertz clock speed, which really on our system usually ends up running at about 3 gigahertz because it turbos up and the cooling is so good it can't. Or on the mic, it's 1.1 gigahertz. Doesn't turbo anyway. Also, the amount of memory. That's a big issue when you move to the mic and you've got all this floating point performance, but now you only have 8 gigabytes of storage. Or on the host, you have fewer cores and more memory. And so these are things you have to consider if you're programming for the mic and trying to balance your code. Here's just a simple diagram of how we have these nodes configured. You have the mic on one PCI bus. If you're on one of the few nodes that have 2 mics, the other mic will be off the second PCI bus, and you also have an IB card on one of the PCI buses. So together, we will call this the node. Later, you may hear someone speak of the node or the host. If they say the host, they're always speaking of the 2-socket Sandy Bridge system, not the mic. So the file system. Stampede has 3 file systems. So there's home. Well, I guess let's talk about the local one first. On each compute node, you have 80 gigabytes available on the temp file system. So if you're executing some sort of I/O that's very intensive, but it's local to the processor, then I advise you to do it all in /temp if it'll fit. And then when you're done, you can copy your results back to the shared file system. This way you won't interfere with the parallel file system and you'll get better performance. Now, we have 3 shared file systems: home, work, and scratch on Stampede. I mentioned work earlier. That's Stockyard, and it's shared among all our systems, and you have a terabyte quota there. Now, Stockyard is not backed up. It's not scrub, but it's not backed up. So anything you want for long-term storage, you should put on Ranch. The Scratch file system is where you should run. That's got the most storage, it's got the most I/O bandwidth. Now, it's called Scratch because nothing is permanent there. If your files haven't been accessed in over 10 days, then they're eligible for removal. So anything you want to keep for a long time, unless you're actively working on it every day, you shouldn't leave it in Scratch. We get tickets all the time where people say, hey, my files are missing from Scratch. Can I get them back? No, sorry. We don't back Scratch up. The only file system we back up is the home file system. And one of the reasons that's the only one we back up is because of the size of the file systems and the amount of time it takes to back up and where to store it. And so on the home file system, you have a 5 GB quota for your home directory. And for the people who know anything about Lustre, we've got the OSTs on the side, and you can sort of correlate the number of OSTs with the bandwidth. And so, as you see, between home and Scratch, Scratch has many more OSTs, much more bandwidth. Now, Work has 672 OSTs, but Work is not part of the Stampede system directly. So Work is an external file system. So although there are more OSTs, there are fewer gateways from Stampede to Work than from Stampede to Scratch. Okay, here's an overview pretty much of what I just told you, except you can see your quota in home is 5 GB, your quota in Work is 1 TB, 3 million files. There is no quota on Scratch. So in Scratch, you can go as large as possible, although be aware, if you start creating tens of terabytes in a very short time, you'll probably be disabled just because you're increasing your files so quickly, you have the ability to overwhelm one of these OSTs. But technically, there is no quota on Scratch. Oh, also, which I failed to mention yet, we have nice little aliases for each of these. So to get to Work or any subdirectory in Work or Scratch, you can use CDW or CDS and then the name of the directory. You have 16 large memory nodes. They're each a terabyte, 32 cores. These are for data-intensive applications and mainly running out of memory. If you have a file I/O intensive application, let's say, and the total file size is less than 300 or 400 GB, you might be able to use the large memory node in a shared memory partition and basically use the memory as a data RAM. We also have 128 visualization nodes, each with a K20 GPU. And these nodes are just like all the other nodes, except in addition to a mic, they have a GPU. They have both a GPU and a mic. So our queue structure has gotten fairly complicated over the years. We have many more queues than we used to have because now we support the mics. If you want to use a mic, you should run a normal mic. If you want to use one of the nodes with 2 mics, we have a queue for that, normal 2 mic. Normal is where most people run. If you need to run large scale, and by large scale, I mean over 4,000 tasks, 256 nodes, you'll have to request access to the large queue. Large MEM does not require special access. Anybody can run there. Those are the 1 TB nodes. The serial queue runs on a regular node, but you get the whole node. So if you need to run serial jobs, if you need to run many, I'd advise you to run at least 16 in one batch job, because you're going to get charged for the whole node. And so what you can do is you can run 16, you can background them in your batch script and have a wait at the end, and the script will exit when all 16 finish. Also, if you need to run a lot of serial jobs, we have a piece of software we call the launcher, which works really well for parameter studies. And you can run that in the regular queues. You don't need to use serial. We also have GPU, GPU dev, viz, and viz dev queues. The dev queues, I think, have X11 and the licenses enabled, where the GPU and the viz queues, I don't think have the licenses enabled. They're for running. not compiling and building. So that's a quick overview of the hardware. We're about to get into more on the software and the tools and program. Time for a break. Well, first, any questions? Quiet bunch. You'll know this. Okay, thanks. We'll be back at 10:30. And Jason will now help me.
Good morning. I guess it's time to continue our training session. So in the following hour, we are going to talk about parallel computing. And it is very likely that this is your first parallel computing course, so I will start very gently. So we'll skip most of the complicated or tedious syntax for a while, and but you will see that in the afternoon about MPI or OpenMP syntax. But in the following hour, we will get the general idea and the basic concept about parallel computing. My name is C. Liu, and I'm working for TACC High Performance Computing Group. And the material we are going to see in the following hour is prepared by me and Dr. Doug James. So in the following hour, we will see the architectures and the programming models provided by parallel computing, and we will see several different levels of parallelism. We will also see some practical and theoretical performance limits, and there are a few other issues and challenges raised from parallel computing world, and we will have a very general summary at the end. So the architectures and the programming models. So I have been in this parallel computing field for more than 10 years, and some of my students ask me, what is the book? What is your first book to learn parallel computing? And I try to remember what is that? Is that the parallel computing, or is that scientific parallel computing? No, I remember that it is this book I first read about parallel computing. It is The Adventure of Tom Sawyer by Mark Twain. And you must have read the book, and you may still remember the story that when Tom is punished by his aunt, and he's asked to paint a big fence, and but Tom doesn't like that. Tom just wants to go fishing with his other friends, and he decided to do something in a trick way. So he tricked several of his friends and persuaded them to paint this fence for him. So instead of painting the whole big fence all by himself, he and his friends complete work in a very reasonable time because they have multiple people working on the same project. So you can assume this is your project. The project is just painting the fence. Like this is your work for your computer to complete. And if you do all the things by one single computer, by one single CPU core, or just by yourself, by one single brush, it will take a really long time. And it's not what you wanted. So you have learned, maybe I can use parallel computing. So you will ask your friends, or you will have more painters or brushes to work together. And that means you can use more CPU cores. You can use more CPU resources to complete the same project. And then you can expect the project to be finished in a shorter time. Or another way, you can paint a bigger brush in the same amount of time. So that is the basic idea of parallel computing. And let's see another story. So in this story, you are going to mow your lawn, and assume you have a big golf field, and the grass is just growing too fast, and you just rent a few mowers, and you are going to do the work. So instead of using only one single mower, you rent a lot of mowers and work on a really big field, and then you can expect the work will be finished in a reasonable time. And or you can just mow a bigger lawn with the same amount of workers or same amount of computing resources. And this story also gives another hint. So assuming instead of working with a really big golf field, you only have a very small backyard of yourself. You just need to mow the lawn of your backyard, and that is a very small field. And since you already learned parallel computing, you already know, okay, I can use more mowers to do the work. You rent a lot of them. But then you notice that your backfield is so small. And once you have like 20 or more mowers there, it doesn't work. They are blocking the way of each other. And that makes your complete work really inefficient. And maybe it's not working at all. So that is the second idea, or second very important concept we get from this story. So if you want to make your parallel computing work really work efficiently, then you probably need a really large work to work with. Otherwise, you will lose some efficiency, or maybe your method doesn't work at all. So we already get the basic concepts of parallel computing from the previous two stories. And please allow me to keep using these metaphors to explain some other important ideas about parallel computing. So in the parallel computing world, there are several different modes you can work with. The supercomputers like Stampede can provide to you. So the first of all, it is called the shared memory mode. So in this shared memory mode, you can think about another metaphor. So you must have played the jigsaw puzzles before, and let's use that as this metaphor story. So everyone has their own tricks to play or have their own method to play the jigsaw puzzles. Let's make it trivial or naive. So your job is just to get a jigsaw puzzle complete. So for every single piece, your work is just to find the right location of that specific jigsaw piece. So assume you have 500 pieces. Then for every single piece, you just pick that piece from the box and then find the location. Maybe it's a corner piece, and then you say, okay, this is the location, and your job is done. And let's assume this is your work. And instead of doing this by yourself, you can invite a few friends and make this jigsaw puzzle work a social engagement. So you invite a few friends and you work together. You put a big box of jigsaw puzzles on your desk, and all these 500 pieces are in that box. And in this shared memory mode, all your friends have the same access method to access these jigsaw puzzle pieces in this box. So every single people, or every single computer, CPU can access these puzzles. And just like you can access the memory, this is a shared resource. This is a shared memory you can use. And every computer, every one of you, every worker has access to that. And in this way, you just work around the table and complete work, and everyone can share the same resources there. And in this method, the programming challenge will be the coordination. So you have to worry about the competition of the same resource. You need to know how to avoid competing for access to the same puzzle pieces or the same data in the memory. And you will learn in this 2-day training the principal programming model for this shared memory mode is called OpenMP, and you probably will learn that tomorrow. And in this shared memory mode, your program should look like this in this picture. A single executable will spawn independent threads and manage threads access to the same amount of data. And that is the fourth method you can use called shared memory mode. And let's come back to the story of jigsaw puzzles. So we have known we can do that in a shared way. How about another different partition way or distributed way? So instead of putting all the jigsaw puzzle pieces in one big box, let's distribute it first. Assume I have 8 friends working with me. Then I will partition the puzzle pieces into 8 boxes. And each box contains some of the pieces. And in this mode, every single people just pick one box of jigsaw puzzle pieces and do their own work by him or herself. And we do not collaborate at this time. So every people or every worker or maybe every single computer will work with their own data and to complete the work or complete the jigsaw puzzles there. And this is called the distributed mode. And the main difference between this one and the previous one is every single worker has its own data, has its own memory, which is inaccessible to all others. And you will see the programming challenge for this mode is a communication. If you figure out, okay, my piece should belong to another people and they can do it easily or quickly, then I need to send him a message. I need to let him or her know that this piece may work for you. So the main challenge here is the communication. You need to send a request or send the data to other workers so they can complete their work. And in the afternoon today, you will know the principal programming model for this one is MPI, the message passing interface. And in the following picture, we will see the model will work like this. So every single assigned core or worker will run a separate copy of the same code, the same executable. And it is normally a rank-aware task, so you can collect data back or you can do some other work in the future. And from this mode, every single core or every single CPU has their own memory access. And let's assume this is a way, and we'll change that in the next slides because of the modern supercomputer architecture. So after we learned the MPI mode and the OpenMP, the shared mode and the distributed mode, and there is another mode which is modern in supercomputer world now. It is called hybrid architecture or hybrid mode. And most of the modern supercomputers like Stampede, Lonestar, and many others will organize their machine in this way. So for every single node of the supercomputer, It is a multi-core shared memory computing running its own operating system. So that means there are few cores. They are on the same node. They can share the memory with each other on the same node without problem. And many such nodes will be connected in a distributed configuration. And if in the pure MPI way, you can think every single core can only see the memory of its own memory, but actually it can see more. It can access the memory on the whole node. So he's just more than himself. For example, on the Stampede supercomputer, there are 16 cores. And if you only use the MPI, the pure MPI, like the distributed way, every single core can access only its memory. But actually it can do more. It can access the whole node memory. So we have learned three different modes to run the parallel computing, the distributed way, the shared way, and the hybrid way. And your programming models may vary. So you can use the pure MPI way in this supercomputer. You can ignore the shared memory, though you have that. As I mentioned, you have 16 cores there. You can share the memory with the other 15 cores, but you can ignore that part and running your code as a pure MPI program. And you can also run your program as a pure OpenMP, but you are confining yourself to one single node because you cannot do anything across different nodes only by OpenMP. And as I mentioned, in modern computers, you can do the hybrid way. You can mix MPI and OpenMP together and take advantage of the whole machine. So why do we do parallel computing? So we know we have the limits of single CPU computing. It is not only the CPU time, but also the total memory, the limits of your I/O, and other issues. So you are going to use, or you're planning to use more resources to complete your work. And parallel computing also allow you to solve the problem that do not fit for one single CPU due to any computing resource limit, or I/O limit, or memory limit. And you can also solve problems with parallel computing that cannot be solved in a reasonable time. For example, you want to do the weather simulation for tomorrow in one day. And if you only have one single CPU to run the high-resolution simulation, it may take several days, and it's just too late for you to do the forecast. So you use more computers. You use more CPUs to complete work, and then catch time. And besides that, you can also solve more cases. For example, some of the people running the Monte Carlo simulation or do some parameter sweeps problems. And if you only have one single CPU or very limited resources, it will take a long time. But if you have a lot of computing resources, you can complete them all at the same time simultaneously, and they will complete in a reasonable time. So that's why you really want to do parallel computing here. And we have seen several different modes of computer we can compute with the parallel computing supercomputers. And now let's see several different levels of parallelism. As a scientist or programmer, what you can do with parallelism, how you can organize your own program. So let me keep using some metaphors to explain the first idea. So let us assume we have some problems, and the problem is just trying to find a needle or needles in the haystacks. And it is a very trivial, or it's very frequently popular problem. And you will see such a problem a lot in like statistics, or linguistics, and genome science. And maybe your work is just to find the maximum value from all your data. Or you maybe want to do an average, or want to do the summation for all your data. Then you just need to go through every single site of data or all haystacks, and you try to find some specific value, or you want to get some statistic result from those data. And a very straightforward or naive thinking about this problem is think top-down and at a coarse-grained way. So you are going to partition the whole work into essentially independent tasks. So instead of going through all the haystacks by myself or by one single computer, I partition the work. I partition the haystacks and working with multiple computing resources. And every single computer or every single core will only need to work with one set or one subset of the whole data. So that is a very straightforward way. And that is called coarse-grained parallelism. So we are going to assign tasks to processors or like CPUs or nodes. And it is very likely the same code will operate on every single CPUs, but they will work on different kinds of data. And the logic within the program may differ across processors because you are working with different data sets. Some of them say, okay, if I meet such a data set, I will do something. And if I'm working with or facing another problem, I will do some slightly different work, but that's okay. So the logic here within the program may differ a little bit. And your main problem is how can handle the communication. You need to know how much communication, coordination, or synchronization you need to complete in this parallelism way. So in the extreme case, it is called massive or embarrassing parallelism. So there is almost no coordination, there's almost no synchronization necessary in your program. And it is a high degree of independence. And some of the important examples are like the parameter sweeps or some Monte Carlo simulations. You just do all the work independently without almost no communication at all. And then you will just given different data sets to different computing resources, and they will just complete the work. And finally, they will report to you saying, okay, this is my result. And you just take care of the final result the way you need. And that is called embarrassing parallelism. And though it is called embarrassing parallelism, it's a great way for parallelism. You will get really great scalability. I'll talk about scalability in a few minutes in this kind of model because all your work are just independent. They are not affecting the other's work at all. And probably on the other side, there's a method called domain decomposition. And this is also a very frequently used and very popular method, very effective method in the scientific or the parallel computing world. So in this way, you have a problem and normally defined on a big domain or big field. And in the domain decomposition, you will partition the field, you will partition the domain in several different processors. And normally, each subfield or each subdomain will be accessed to one or a few CPU or computing resources to work with. And the key issue for this way is the dependencies across the ghost or the halo or the boundary regions. And there are going to be a lot of communications between or among this boundary field, and you really need to worry about those stuff. And to taking care of the communication will be your key issue for this method, and it may also slow down your program because you need to wait for some other people to communicate, to send the information they collected and give it to you. And another issue in this method is the load balance. Sometimes you need to worry about the work on every single domain. You try to balance the work. So every single CPU or every single subdomain problem can be handled in a reasonable same time. So I also list a few examples here, and if you are interested, I also have the links to the specific problem. You can take a look in the future. So that is a top-level parallelism. And let's go to the very bottom level and see what happened at the very bottom level. And normally this is called fine-grained parallelism. So let's take a look at this picture. This is a complex harvest machine. And traditionally, this machine can cut and collect weight for one specific column. When this car drives around your field, and will cut and collect the weight at one single column. And then this machine is invented, and instead of just collecting one single column, you can see the front end of this machine, it can collect several columns of weight at the same time. And that is the idea of this fine-grained parallelism. So by replacing this single column collecting machine with a multiple collecting machine, there's no extra cost, or at least very small cost at all. So you can use this same machine and with the same cost, but do a lot of work at the same time instead of just one single column. And that is called vectorization. So assume you have a big array. You want to do AI equals to BI plus CI. And instead of doing one element at a time, you can do multiple the same work of this at the same time without extra cost. So this is the C syntax and the function syntax for this way. Assume you have a really long inner loops with a few familiar array calculation, like aside C just equal to A plus B. And instead of doing this from I equal to 0 to I from to a big number, you just write this as an inner loop, and then ask your compiler, like the Intel compiler on our machine, to do the vectorization for you. So instead of doing one after another, the compiler will know, okay, this is a really good part. There's little dependency in this loop work, and then I can just vectorize at the same time. Assume I have 1,000 times. If I is equal, if the lowercase n is equal to 1,000, like the array size is 1,000. So instead of doing 1,000 times, you can just divide this by probably 8. If you can do 8 vectorization work together, and it's just be 1,000 over 8. You speed up the same work just by this vectorization trick by 8 times. So that is called the vectorization. And specifically on the Stampede machine, so we provide the Stampede machine which has a vector units. So for every single core of Stampede, it has 2 256-bit vector units, and it supports the floating point addition and multiplication. Each of these units can produce up to 4 double precision results per computing cycle, and together they will produce up to 8 double precision or 16 single precision results per computing cycle. And that will speed up your work at least 8 times or even 16 times if you do single precision work. So we have seen the very top level parallelism and the very bottom level parallelism, and there are still some things in between. And we normally summarize as a medium grade parallelism. So normally you have a really long or really complicated program, and your algorithm normally consists of a number of steps. And some of those steps include loops that may be a very good candidate for parallel computing. Maybe you didn't notice that or didn't aware that at the very beginning time. But there are some steps. And these steps, you can say, okay, I want to parallelize this small step. So in this example, I have work like computing the gradient force and then solve for momentum and computing fluxes and do some other work. And one of the steps is just for every single cell of the whole problem, I want to find the critical point. So the critical point means I want to get the point where the gradient is 0. And because these cells are independent, some kind of relatively independent, I can do this step in a parallel way. And normally we can use some other method like the OpenMP to do the parallelization for that step. And here is the summary of what we have seen about these different levels. And you need to know that it is not the only way to complete work. For all your program, you can parallelize your program in several different ways. Some of them may perform better, some of them may be a little slower, or maybe not a good idea. But there are normally more than one way to complete the same work. And it doesn't necessarily require the hybrid or the OpenMP plus MPI method. But this is just the general idea people do when they are facing some complicated problem. And the normal or this frequently used method look like this. So you have a really coarse-grained parallelism across all your nodes or CPUs through the MPI tasks. So every single MPI task will do some work on the task level. And when there are some steps or small loops or small steps you need to handle, and you believe that can be parallelized, then it is called the medium-grade parallelism. You normally use OpenMP because it's more easy to complete that work within one single node. And then at the very bottom level, you have you normally have a lot of computation. You have a really computing intensive loops at the very end, at the very bottom level. Then you are trying to vectorize this part. So we have seen the different levels, and we also present how we normally did as a scientist or a programmer. And besides that, you can also use some existing tools. So there are a lot of libraries and existing tools developed and optimized a lot by some really experienced users and developers. And instead of doing all this work by yourself, you can use them directly. You can use them from the existing tools box or libraries. Some of the frequently used libraries include the Intel, the mice kernel library, or known as MKL, and it has robust support for mic. You have seen that we also have the mic machine, the mic coprocessor on the machine. So you may use MKL library for your CPU work or even for your mic computing work. And some other libraries called PATI, it is a dense and sparse object-oriented solvers, and there are a lot of others. So you can use those existing tools. So do not invent your own tools unless you are really good at, or you can do it in a reasonable amount of time. So call those things directly. And for example, you want to do some matrix multiplication or matrix vector multiplication, or you want to solve some linear system. So do not do it again by yourself, unless you are just doing that, unless it is really your own research work. If you just want to do something like solving a linear system in your complicated source code, then you should think about, I called an MKL function to complete work first, instead of solving the system by myself. So that is several different levels of parallelism you can use. And next, we are going to see some practical and theoretical performance limits of parallel computing. So we assume you are like programmers or scientists working with your own program, and parallel computing is more kind of your tool. And you are going to use parallel computing to complete work. And normally when you try to write a proposal or when you try to complete a paper, besides the scientific results, you normally also need to provide some kind of performance result or core scaling result. And just convince the people, okay, my program works correct based on those scientific results. And also you are going to provide this kind of scaling or performance results to show people or to persuade people, okay, my code works fine on parallel computing, and I can use the parallel computing to complete work faster or to complete a bigger problem. So that's why you normally provide this kind of scaling result as well in your paper or proposal. And the most important one is called strong scaling. So when you have a problem to solve, and you will fix this problem size. So you have a problem size fixed, and you are going to enroll, or you are going to use more computing resources. You are going to use more nodes or CPUs to do the work. And there are two basic metrics for your performance normally. The first one is called speed up. So assume you are solving a problem with 1 CPU, 2 CPUs, 4 CPUs, and more, and we just increase the number of CPUs enrolled in this work. And we are going to count, we are going to calculate the time you spend on this program. And the speed up of the matrix is defined by the time on one single CPU or one single processor divided by the time on P processors. So it's going to be a number bigger than 1 normally, because if you're just doing one single CPU, maybe you'll take 2 hours. And if you are going to use 2 CPUs, maybe the ideal case, you only finish the problem in 1 hour. So your speed up will be 2. So that is called the speed up of P processors. And from the pictures on the top, we will see, in the ideal case, each time you double the number of processors, you should halve the total computing unit in the ideal case. That is your goal, that is your target. That normally cannot happen, but that is your goal. And practical, you will get some called sublinear speed up. So you will see this, you will normally get this red line in your own project. It is close to the ideal speed up line at the very beginning when the number of CPUs is small. And as long as you increase the number of processors, you have more throughput, you have more things to worry about, you have more communication to take care, then you lose some speed up. And that is normally a practical line you will get in your future work. And the second metric for this performance result is called efficiency. So the efficiency is just defined by the speed up SP divided by the number of processor P. And you can assume in the ideal case, the efficiency is always 1 or 100%, no matter how many processors I'm going to enroll in my computation. But that is only the ideal case. As I mentioned, you have another things to worry about for the parallel computing, and there are other stories that will hurt your performance. So normally you cannot get the perfect or the ideal case. And it is very likely you will get a result in the right line shown in the bottom picture. So I believe I have already covered all the things here. So the reality set in the expect to lag behind perfection. So you never get perfection or the ideal case in most of the cases. And you can expect a sweet spot. And beyond that spot, even you add more processors, you cannot get any benefits in the computing time or the performance. And there are normally a lot of reasons, and the main reasons for the slowdown of your performance include the various kinds of overheads, communication costs, some load imbalance, some I/O issues, and many more. You have your own parallel computing issues that will slow down your performance. So now let's see a true story, not a true story, but let's see a metaphor to see what happened there. So assume I want to bake a cake. So how fast can we bake a cake in the parallel computing world? So assume for this work, I need 2 hours to prepare the cake for baking and another ½ hour to bake the cake. So the total time of this work is the 120 minutes, the preparation time, plus the 30 minutes bake time. So that is at least 150 minutes for myself if I want to cook it by myself. So we have known we can use parallel computing idea, and we'll do it in a parallel way. So how about we have 2 cooks? And assume we have 2 perfect cooks that can complete work, and they can work together. There will be no waste of time. There will be no overhead between them, and everything should just be perfect. And what will be my time to cook this, to bake this cake? So I can cut the preparation time to be half. So instead of doing 120 minutes preparation time, I can only use 60 minutes to complete this work. But I still need to bake the cake, and there's no way I can bake the cake. I have 2 cooks, it doesn't help. Then the cake still need to be put in the oven for 30 minutes. Then this work takes 60 plus 30 minutes, that will be 90 minutes in all, for 2 perfect cooks to complete this work. So how about we have more cooks, more perfect cooks to complete on the same work? So for example, you can see I have 5 cooks, and then the preparation time will be cut into 120 divided by 5. That is about 24 minutes. And then the total time will be 24 plus 30. That is 54 minutes. And if you, besides doing the calculation about the total computing time, let's also do the computation for the speed up and the efficiency. And you will see I have perfect speed up for 1. It doesn't, I mean, that's always 1. And for 2 cooks or for 2 CPUs, my speed up will be 1.7. And I will increase the number of cooks and keep increasing my speed up. And you will see my speed up ended at about 4.2. Even I already have 20 cooks there. It increased only a little bit, as long as. And if we take a look at the computing time, as long as we have more cooks, then the time is close to 30 minutes. And the efficiency, for the efficiency, that is a third picture. And we begin to lose efficiency when we increase more processors or more cooks there. So what we get from this story? So we get from this story, there are some limits for my speed up or for my efficiency. So I have 120 minutes to prepare the work. And those kind of work can be perfectly parallelized. So as long as you have more people or more CPUs to work on this section of work, then you can expect you will decrease the time a lot. And this part will be really parallelized, and you will get really reasonable speed up or efficiency. However, you remember that there are some time or there are some work which cannot be parallelized. For example, in the story, I have 30 minutes of cooking time, of baking time. You need to put the cake in your oven for 30 minutes. And no matter how many cooks you have, you still need to take these 30 minutes to complete this session of work. And that is things you need to worry about, or you need to pay much attention in your own work. So assume we can partition our work into 2 or trivial 2 sessions, the sequential part and the parallel part. The sequential part is just like the baking time, 30 minutes. There's no way I can parallelize that. And then the rest of work, I assume I can perfectly parallelize those things. And we just partition the complete work into these 2 sessions. And we use the lowercase ts and the lowercase tp to represent the time you need to spend on the sequential work and the time you need to spend on the parallel work. And if you do some basic math calculation, the speed up is defined by the capital T1 divided by capital TP, the time on one single processor or one CPU, and divided by the time on peak processors. And we know that the parallel computing and the time of TP can be divided by P because those work can be totally parallelized perfectly. And if we divided this by P, and then SP is equal to TS plus TP, that is one single CPU case, and divided by TS plus TP over P. And that is the time spent on P processors. And if you take the limit and make P goes to infinity, and you can drop the last term. And that will be defined as TS plus TP over TS. And normally it is called the reciprocal of the serial fraction 1 over alpha, because alpha is defined as TS over TS plus TP. And that is a very important limit or very important law in the parallel computing world. It calls Adam's law to describe the limit of your strong scaling. So no matter how many processors or how many CPUs, how many workers you can work with, there will be a limit coming from the serial part of your work. So if you have a lot of work that cannot be parallelized, you cannot expect your speed up to be a really reasonable number. For example, in the right picture, let's see the right one where the serial fraction of your work is 20%. Assume 20% of your work cannot be parallelized at all, and then alpha is defined to be 20%, 0.2, and you will see the scalability of this problem will be bounded by 1 over alpha, which is 5. So if you have 20% of a work that cannot be parallelized, then you can never reach a speed up over 5. So that's a lot. So just pay attention. You need to try to make all your work to be parallel. Otherwise, your speed up or efficiency will not be a reasonable or a good one. So I already explained all these pictures and the summaries and the reasonable assumptions. The serial fraction is a severe constraint of your program or your code. And you cannot run faster than the serial time. And as you add more processors, you reach a point of diminishing returns. And as I mentioned, the speed up is bounded by the reciprocal of the serial fraction, which is very important. You should always keep that in mind. And always have a good estimation of your serial work percentage, and you will have a really good estimation of your speed up and efficiency for the program. So that is called strong scaling. And sometimes you cannot do strong scaling because maybe the program is just too big for one single CPU or for a small number of CPUs. And to solve this issue, people define another performance scaling. It's called weak scaling. So instead of defining a problem to be a fixed problem, you can change the problem size as well as the number of processors you work with. So for example, you want to have one single core to work with 500 pieces of to work with 5 square feet. And then maybe instead of just fix this 5 square feet problem and increase the number of processors, you have like 1,000 square feet problems and divided that into 2 processors. So you increase the problem size in proportion to the number of processors you have. And we still want to know how big a problem we can solve in the same time as the serial problem. That is called weak scaling. So you sometimes can just report your weak scaling result once the strong scaling is not possible. And similar to the strong scaling, it is a limit there. And the name of this rule is called Gustafson's law. And by this law, the speed up is bounded by 1 minus alpha times P. And the efficiency is defined by or bounded by 1 minus alpha. So if you have a really big alpha, if you have a really big proportion of your serial code, then your efficiency will be really bad. So just always keep in mind. And you should pay much attention to the serial fraction of your program. So if you do some I/O which cannot be parallelized, if you do some like complicated preparation of your program or complicated data processing at the very end of your program, which cannot be parallelized, then you will lose a lot of your performance and the speed up there. And this is just a picture of the Gustafson's law. When you have a really big alpha, when you have a really big serial fraction in your code, then the efficiency will be really bad. So here is the practical and the theoretical performance limits of this parallel computing. And there are some other issues and challenges you are going to face when you program with parallel computing. So the most important thing is the correctness. And you have a program that works perfect before, and you just say, okay, I want to make it faster, or I want to have a really parallelized code. Then you just begin to program with parallel computing with either MPI or OpenMP or hybrid way. And now you notice that your program may be run. They can run fine, but maybe it didn't give you the right result. So your program will or may happily execute your incorrect code without problem, but you will see, okay, the result is not what I expect. And normally the game is to, and normally it happens a lot in the parallel computing world. Then there are a lot of reasons for that. Some of them, maybe you have some race condition issues. You will see probably in the afternoon, and probably you will see some truncation error because of the ordering of your computation or some other issues. That will lead you to a different result. And the second issue is the independence. And as I mentioned, when you do a parallel computing, and most of the time you need to take care of the dependency or the communication. And normally the game is to identify the independence and manage these dependencies. So the ordering of your code and the ordering of each section of this code, and also the communications, the ordering of the communications are particularly important when you have a parallel computing world. You will see that this code cannot be run in any random order. It's going to give you a wrong result. And your main job is just to identify these independence or dependencies there. Let's see a very trivial, straightforward result or example to understand this. So assume I just want to do some easy summation here. I have two vectors B and C, and I just want to get summation of B and C and assign the value to another vector A. And you can see this is totally independent and safe. No matter what ordering I use to do the calculation, then the vector A will have the same result. Because if you just want to calculate A0, it only depends on B0 and C0. And if you want to do A100, it only depends on B100 and C100. So no matter what ordering you are used to make this calculation, it will give you the same result without problem. However, let's see some complicated work. So in the second case, I want to do AI is equal to AI minus 1 plus AI plus 1. So A1 is defined to be A0 plus A2. And then A2 is equal to A1 plus A3. And now you notice that if I change the ordering of this one, if I do A1 first, then the result will be one result. However, if I do the A2 result first, and then the A1 will use the new updated A1 I already get, and the result could be different. So for this kind of loop, it is not safe to do the pure or the naive parallelism. You need to assign a specific order. You need to tell your system or code, I need the right order to do this computation. And of course, this one cannot be parallelized. By the default setting, you will just start that by the loop ordering defined there. But if you want to define a parallelism way to finish this computation, you need to remove these dependencies, or you need to tell the computer, the compiler, to do that in a specific order. And this one, we can easily figure out this is not safe. And how about the third case? So in the third case, it is also a very trivial operation we did a lot. So we want to switch the value or swap the value of A and B. And you believe that this must be safe. Is that true? So we can see we use a value called temp. We use a variable named temp. And temp is used to help you complete this switch. And you will say, okay, my AI and BI value do not depend on any other AI and BI value. So if I want to swap A0 and B0, and no A1, A2, A3 will be involved, it sounds correct. But pay attention to this temp variable. So if this temp variable is a temporary variable, but it is shared by all your CPUs or computing resources, then you could be in trouble. So for example, one of the processors just define temp equal to a value. And before it swapped to the other value, before this temp value assigned to B, now another processor come to this code and saying, okay, I want to assign A1 to the same variable, and this temp value has been changed. And you are trying to assign a wrong value of temp to another BI. And if you try to parallelize this code, You can do that, but it's not safe because this temp may not contain the exact value you want it to contain for every single loop. So this is just the very trivial case, and we can figure out, we can understand very easily. But in the practical world, your code will be really complicated. So when you learn OpenMP or MPI in the afternoon and in the tomorrow, pay attention to those variables. Can this variable be shared? Can this variable cannot be shared? So pay attention to those things, and also pay attention to those things in your own program. And it will save you a lot of time for debugging your own code bugs in the future. So as I mentioned, the correctness and also the repeatability is very, very important in parallel computing. And the repeatability is going to be a great debugging challenge. Sometimes you just run the code and you run it tomorrow, you get a different result. That happened a lot. And also some of the code may work sequentially and then fail in parallel. And some worst cases, some of the code runs fine with maybe no more than 100 processors. But if you increase the number to 400 processors, then the code crashed or you get wrong result. And the behavior may vary from one run to another. So everything could happen there. And there will be no magic bullet for all those kind of challenges. But there are some general advice. So first of all, yeah, this is my colleague Doug suggests. So try to avoid temptation to blame the environment. And normally, like more than 90% of the case, it is not the problem of the system. It is a problem of the code itself. And to solve these problems, you need to learn some extra tools, particularly some debugging tools. So you may have learned how to use debuggers like a GDB or IDB, and you probably need to some advanced tools. Some parallel debugging tools like DDT, probably you will learn tomorrow as well. And use those debugging tools will save you a lot of time to debug those parallel code. If you just run some print in your code, it's going to be really complicated and it doesn't help, or maybe not efficient most of the time. And when you program parallel computing, remember to test your serial and the parallel behavior regularly. So once you complete one small section of your code, each time you complete one single section of your parallel computer code, just do some test and make sure that section is correct. At least you believe that is correct at that time. And then in the future, you can combine them together. And hopefully that will save you some chance to get a bug-free code. And always test on small test problem first. And if your program crashed on small test programs, and it is not very likely to work for big problems at all. So that is some issues and the challenges you are going to face for parallel computing. And before going to lunch, let's have some quick summary of what I've learned in the past hour. So we have seen several different ways you can do parallel computing, and the machine like Stampede supercomputers provide several different modes you can work with. The shared mode, distributed mode, and also the hybrid mode. And normally, the shared mode comes with OpenMP programming, and the distributed memory mode comes with MPI programming. And there will be some limits of your performance. There will be a limit for your scalability and for the efficiency of your program. It depends on the fraction of your serial code in your whole program. And you normally can expect a sweet spot. And besides this spot, you get almost no performance at all, even if you increase more processors to work with. And since you already decided to work with parallel computing, and it's a good idea to use parallel computing or supercomputers to complete your serial code now. And there will be some work ahead, but it's going to worth the effort. And you will see that you can complete work in really reasonable time or do a really big program in the same amount of time by using the parallel computing in the proper way. I believe that is the end of the presentation. And if you have any questions, and I'm glad to answer all those questions. And otherwise, we are done here, and our afternoon session will be back at 12:30. Thank you.